SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. Let's continue our discussion on this method of weighted residuals, the weak formulation. Yesterday, we wrote down some of these equations towards the end of the last class. And let's continue that. There are many important aspects of that which will form the basis for our finite element formulation. So just to put the things, so this is the heat conduction problem. We'll take the heat conduction problem in 2D and illustrate this method with respect to a heat conduction problem in the domain omega. So which has the important part here is that this is the governing equation and these are the two boundary conditions, phi is equal to phi bar on a part of the boundary where the temperature is prescribed. So that's, we call it as gamma phi boundary. And on the other hand, there is another part of the boundary where the flux, that is the heat leaving the boundary, is defined as Q bar. So on gamma Q. So the thing is that we want to get into the weak form. We studied that to some extent. Particularly this weak formulation becomes very powerful, particularly while applying the boundary condition using the derivatives. In particular, we are talking about this one. The other boundary condition phi is equal to phi bar, which is not very difficult to implement. So what we are doing in the weak formulation is that this is the first integral here is the residual on the governing equation. So that means that not satisfaction of this governing equation. So whenever there is a residual, so there is, you will make it in a overall sense using the weighted residual function Wi. And then in addition to that, so we will also add here another term, boundary term, which involves the derivatives. So this is particularly the heat flux boundary condition, where this k dou phi by dou n plus Q bar. So this is, that means that the phi bar is not getting satisfied this boundary condition. So that also now is taken as a residual, where this Wi prime is another weighting function. And this set of weighting function may be same as Wi or may be different or may be related in some way. Okay. So let's look at the approximation for this phi hat. The phi hat, as we assume it here as a series expression where Aij the undetermined coefficients and psi j and psi naught are known functions in such a manner that this satisfies the gamma phi boundary condition. So gamma phi has to be, phi hat has to be phi bar on gamma phi. So that is possible by taking psi naught to be phi bar and all these psi j's have to be 0 on gamma phi. So you can very easily see that by putting these things here, so this phi hat satisfies this temperature boundary condition over gamma phi, whatever be the value of these coefficients Aj's, undetermined coefficients Aj's. So now what we are going to do is that we will try to simplify it by doing the partial integration. So we did this to some extent. So if you do this partial integration here, doing partial integration here, integration by parts. Okay, so this one here, a integration on omega will become a partly an integration over gamma and partly over omega. So by doing this rule using the Green's lemma, so this can be converted to, so using, if you want, you can refer to Green's lemma in 2D, in which case this becomes Wi dou phi by dou x times nx and w. So I will write this both at the same time. So this is over gamma. So that means that these two terms will result in an integral on the boundary, right? And then it also will give you with a negative sign here on omega, that is dou wi by dou x k dou phi by dou x plus I still write it as d omega, so it can be dx dy. If whenever you need it, you can put it, or it can even be some other type of rd theta, rdr, whatever you want it. So this is taking these two terms, and then this term will appear as it is. And together with this, the last integral over, this integral need to be evaluated only for the boundary condition where this gamma q is there. Forgot to put that q here. So that will continue here, wi and k. I'll split it up, dou phi by dou n t gamma. I'll split it up into two terms. Okay, so this will take care of all the terms, right? So this is nx and ny, as I was telling you yesterday, is, so if there is the unit normal to the boundary, so this nx and y are nothing but the directional cosines of the normal. You can even say that it is cosine times angle here for nx, cosine times angle here for ny. So that's how they are defined. All right. So if that is the case, so here the first term here, let's just simplify the first term, and that is like this one. So I'll just take wi common, dou phi by dou x, nx dou phi by dou y and y. So this is first term, and which can be simplified as, so this is the derivative in the x direction multiplied by nx. So derivative in the x direction multiplied by this nx, and the derivative in the y direction multiplied by ny here. Both of them combined together as the derivative. There's a k here, of course. There's a k also here. Forgot to put that here. Okay, please. K here. Okay. K also here. So this can be written as dou phi by dou n d gamma. So this gets simplified as this derivative with x with nx plus derivative in y multiplied by ny, both together will form as derivative of phi hat in the direction of n. Okay, so that is this part, and then this stays as it is. So now let's rewrite this statement. So rewriting the above equation, putting this in this equation, putting this in the above equation. So what we get here is that it is gamma wi k dou phi by dou n d gamma. So this is the boundary integral minus dou wi by dou x k dou phi hat by dou x So this is this part, and the rest of it will just continue as this is over omega, and this one here wi bar k dou phi by dou n gamma. This is over gamma cube, right? And then there is another here. Okay, this is equal to 0. Looks a little long, but then we are going to make it simpler by looking at this one. So this is the first integral here, wi k dou phi by n. This integral actually is over the whole gamma. So we can even write it as gamma phi plus gamma cube. You understand here? This one, this is I can replace the whole boundary here by gamma phi as well as plus gamma cube. Both terms will be there. So why we are doing this one is by looking at the other term, which is exactly similar to this one. Here this term is there, wi prime k dou phi by dou n d gamma. So now you can immediately find out that something can be done. In fact, we can cancel these two, this term here and this term here, which I am marking with this yellow block. So you can see that these two can be cancelled, okay, by appropriately choosing. How can we choose? There's a wi prime here and then there's a wi here. So by appropriately, by choosing wi prime is equal to minus as minus wi. So we can cancel the boundary, the integral over boundary gamma q of k dou phi by. So we have k dou phi by dou n here and again appearing here k dou phi by dou n. So by choosing this wi prime as minus wi, so this integral over gamma q can be cancelled. Okay. So then that means that this here gets cancelled with not the complete part, because this is both gamma phi and gamma q. So only this gamma q disappears. So then we can simplify the whole thing now as so this is left out with only gamma phi, and we have this. So the other terms stay as they are. And the other terms are, so we can, so if you choose, so if you are choosing wi prime is equal to minus wi, so that will equally apply to the last term here. So we will put it as a minus wi q bar, and this is for gamma q. Okay, so this is now simplified to some extent. I'll just write it. Okay. So we are still with a boundary term here on gamma phi wi k dou phi by dou n. So if you use the Galeckin procedure, Galeckin weighted residual procedure, so wherein, so what is that Galeckin procedure? So in the Galeckin procedure, we choose the weighting functions same as the trial functions. So what we are saying that wi we are choosing to be I, right? We are choosing wi is equal to psi I. So what is the, if you go back and look at what is psi I, so you can definitely see that what is the value of psi I and gamma phi. So phi hat has to be chosen in such a manner that psi naught is equal to phi bar and psi j has to be equal to 0 on gamma phi. So if that is the case, then this implies which is equal to 0 on gamma phi. So if that is the case, so that means that this integral here, so this is going to be 0, this is equal to psi I and equal to be 0 on gamma phi. So that means that, so this term also now disappears, so leaving only this one here, right? So now we can rewrite this whole equation, collect the terms properly. So we'll just collect the term wi is equal to ci. So there's a negative sign and then this plus minus. If this rearranging, then we have, so I will replace this now as I and this as phi hat for the moment. So this is on the left side, and on the right side we have these things. So this is the heat generation part, and here we have psi I, q bar an integral over gamma q. Okay. So this is what is simplified form. And then using phi hat to be, of course, it is there as we have the term psi naught also. So let's use this one. So then what will happen in the phi hat? We also get psi naught, and which is a known function, and then that can be taken to the right side. Okay. And then, so let us, and then this aj Sij stays here. So let's just collect all the aj terms. So what we have here is dou psi I by dou x. So I'm putting this. So this is this part. And then on the psi naught part, we'll take it to the right side. So with a negative sign. So I'm collecting all the terms. And this is with a negative sign. Obviously, this psi naught, when you substitute it here and take it to the other side, so you'll have that, and then together with the two other terms. Okay, so this is in a longhand. So this is what the algebraic equations in terms of aj. So we can even just simplify it a little bit. So I will just simplify it a little bit as aj Kij is equal to bi, where j goes from 1 to n. This Kij is the matrix of K in that matrix, where Kij is just given by I can write it as dx dy if I need it, or sometimes I write it as d omega. And this is Kij, and bi is the one on the right side, which we have written here, is so this is the complete set of equations. Okay, so this is the, in a nutshell, this is the set of, this is the ith equation, right? Why do we call it as ith equation? So by putting psi I here, psi I, so we will get this equation and using different values of psi I, psi 1, psi 2, psi 3, psi 4. So you will get as many equations as there are n terms. So you can, if you want, we can even put it in this form. So I'll just caution you, please don't get confused this one. This is a matrix of coefficients k, okay, whereas this small k here is the thermal conductivity. So please. So we use this k here in this expression for in tune with the stiffness matrix and maybe the displacements and forces. So this is the general expression for these algebraic equations. So you can very easily see that the whole problem has been put into this final form. So where this k is a square matrix of n by n if there are n coefficients, and then there's n vector here. And then this kij, you can say that has been given by this one by taking I and j different values. So you will get this k coefficient. And similarly here, b is a vector. So bi depends upon psi I. So bi depends upon psi I, psi naught here. And this is q. This is the heat generation within the body. And this q bar is the heat flux leaving the body over gamma q. So this has to be integrated only over gamma q, right? So very interesting facts here. One is that this is a weak formulation, as I was telling in the last class, is that the phi hat to start with only requires a lower order continuity condition, right? So because in the strong form, we had used L here, right, for phi hat. So if L is second order derivative, so then that means that it should be at least second derivative existing there. So which we call as C2 equation. The second derivative should exist. The function should be non-zero or without any discontinuities, right? So whereas here in this one, what happened here in this weak formulation, so what we are able to achieve is that, so the phi hat need to be of lower order discontinuity because the derivative order has come down by 1. Okay, that's number one. Number two, the advantage of the weak formulation is that we are able to take the residual on the derivative boundary condition into the weighted statement, and we are able to cancel the evaluation of the derivative on the boundary of that derivative with the derivative term which has come out of this integration by parts. So finally, so this is a very appealing representation of the weighted residual in the weak form. Why? Another very important fact here is that by choosing this Galectin procedure, so what we are able to achieve is that this coefficient here, these coefficients, and then this matrix turns out to be symmetric. You can see that the I and J, even if you interchange, the value will not change. So which means that Kij and Kji are same. So that way K happens to be a symmetric matrix. So this offers a very tremendous advantage as far as our computations are concerned, because one thing is the storage roughly becomes half of it, as well as there are very powerful algorithms which can handle the inversion or the solutions of the symmetric matrices, in the sense that, so if you use this one, the amount of time that is taken for solution of the symmetric matrices is just 1/6 of a fully populated, or even 1/8 of the fully populated K matrix. Okay, and further, of course, there are also other advantages later for the. So I hope you are able to appreciate the various stages of formulating this method of weighted residuals. So first of all, we started with only the strong form. Then we went into the weak form. Then we also included a boundary term, which is in particular involves the derivative boundary condition. And then finally, we have arrived at a very appealing presentation. So where the K matrix has a very simple expression like this one. And B, of course, is slightly longish, but it's also very simple. And this turns out to be a symmetric matrix. Okay. So I think I'll stop at this thing and then I'll take up an example in my next class. Okay. Bye.